In section 5.1, we think about how to calculate the area under a curve. And whenever we say the area under the curve, generally we mean the area between the curve and the horizontal axis. So here it's under this function f of x, but that means under f, but above the horizontal axis. So we're interested in figuring out this area, which again, if you think about it, so we know how to find the area of a circle. We know how to find the area of a trapezoid. We know how to find the area of a triangle, right? We've not thought before about how would we come up with the area under a curve. I mean, if the curve was a straight line, that would be pretty easy. But when it's not, as in this cubic function, how do we go about doing that? Right? And you may be asking yourself, why would we want to? And we will get to that. But for now, let's just say we want to find a way to do it. So in this case, we're interested in looking at x's between 1 and 3. And as it says, we partition the interval into n equal subdivisions. And the width of each subdivision is called delta x. And we can find that by calculating b minus a over n when our input interval that we're interested in is from a to b. So I hope that this makes common sense to you, and I'm going to go over it with this example. So like if we want 4 partitions, right? So first of all, our a value is 1 and our b value is 3 in this example. And our delta x then, we're taking the distance from 1 to 3, which we get by doing b minus a, or let me just put the numbers right in. Right, so it's a total width of 2, but we want to divide that into 4 equal pieces. So each piece is going to have width 1/2. So that will be our delta x. So it says create the partitions in the left-hand rectangles on the graph here. So going from 1 to 3 by subintervals of 1/2. So let's think about our first subinterval. Because it said we're using left-hand rectangles, our first subinterval is from 1 to 1.5. We're going to use the left endpoint of that to create the rectangle height. So I'm going to actually erase and draw this over, but I just wanted to show you where that was coming from, and mine was a little crooked besides. So when I look at my subinterval from 1 to 1.5, I use the left-hand piece of that at 1 to go up to the function, and that creates the height of my rectangle. And then my second subinterval is from 1.5 to 2. So I'm going to go to the left end of that at 1.5 and go up to the curve. That's going to create the height of my rectangle. And then my third subinterval is from 2 to 2.5, and I'm going to go to the left end point at 2 and go up to the curve, and that will create the height of that rectangle. And then I'm going to take my fourth and final subinterval from 2.5 to 3. I'm going to go to the left end point at 2.5 and go up to the curve, and that will determine the height of my rectangle. So I've created 4 rectangles, and what I'm going to do then to estimate the area under the curve is I'm going to find the area of these 4 rectangles, and I'll call those areas A1, A2, A3, and A4. I'm going to find the area of each rectangle and sum those up and use that to estimate the area under the curve. Now you probably can already see, and you might be questioning, wait, there's some area we're not getting, right? What about this area? What about this area that's under the curve? What about this area? What about this area? And you're right, and we're going to have a way to deal with that soon, so hold that thought. Okay, it's a good thought. Just hang on to that, and we'll get there. Okay, so for now, for example, if I want area 1, so this is a rectangle, and I know the area of a rectangle is length times width. In this case, it's going to be helpful to think of it as height times width. Okay, and the height of the rectangle is actually, this function is f of x. The height of this rectangle is f of 1. And the width, and the width, as we already said, is a half. That's delta x. Right, so here I'll put delta x in first. And how do I know what f of 1 is? Well, I have the formula for f. I can simply plug in 1 for x, and I'm going to get 7. And delta x is a half. So I get 7 halves, or 3.5 if you prefer. And that is the area of rectangle A1. Okay, then let's do another one. Area A2. Again, it's a rectangle, so I know the area is length times width, or I'll call it height times width. So the height I'm interested in now is f of 1.5. Right, so again, the height of that rectangle is the value of the function right here at x equal 1.5. And then I'm going to times that by my width delta x. And in this case, you can't just probably do this in your head, but there's a table underneath, or you could put this formula in the function f into your calculator and go to the table. But f of 1.5 is 12.375, and delta x again is a half. And if I multiply those together, I get 6.1875. So that's my A2. Now, in Mathematica, I created a table, so this would be more automatic. So in this table, the f of x value is the height, and the delta x is the width. And so when I multiply those together, my last column here is area, that is height times width. Now you'll notice there are 5 rows in this table, but I'm only using 4 rectangles. Well, in my first subinterval from x equal 1 to 1.5, this area at the left endpoint of x equal 1 is my A1. And in my next subinterval from 1.5 to 2, it's the left endpoint at x equal 1.5 that determines the height, and that gets me my A2. And so here's A3, and here's A4. And I'm not using the last value in the table, but soon we're going to use right rectangles, and then we'll see that we will need that last piece, that last row. Okay, so the values in the last column represent areas of rectangles, and the ones that I've denoted there with A1, 2, 3, and 4 are left rectangles in this case. And so the way we can estimate or approximate the area under f between x equal 1 and x equal 3 is to sum those areas up. Sorry about that. We can sum up the areas. So A1 plus A2 plus A3 plus A4, that is 3.5 plus 6.1875 plus 10.5 plus 16.8125, and you can double check me on this, but I believe if you were to add those all together, you'd get 37. So 37 is an estimate for the area under the curve, and note that this is an underestimate. In other words, we could see that there is some area under the curve that did not get captured by these rectangles.